Welcome back to another video of our course method theory for probabilists. Last time we introduced set systems, semi-rings, rings, and sigma algebras. Today we are continuing with this. We are going to define generators and extensions. So when I have a semi-ring, I can extend the semi-ring to a ring, and I can extend rings to sigma algebras. Basically, how that works and how that can be done is the topic of today. So let's start with a small recap from last time. In particular, I will need semi-rings, rings, and sigma fields again. So we said that a semi-ring is an intersection stable set system with this funny property here. A ring is union stable and set difference stable, and a sigma field is sigma union stable and complement stable and contains also the whole set. We will need this today because for these generators and extensions, as I call this here, we start off with these two definitions. So you have some C here, some set system, doesn't have to fulfill anything at the moment. But from this here, I can generate a ring and I can generate a sigma field by intersecting all rings which are bigger than C. Here, for example, and I can intersect all F, but that's a typo, that has to be the same F as here. I can intersect all sigma fields which are bigger than C. In an exercise, you will prove that the intersection of rings is a ring and the intersections of sigma algebra is in sigma algebra, which means that the right-hand side here is a ring and the right-hand side here is a sigma field, which means I really have to find a ring here and a sigma field here. So that's quite abstract. Let's have one example. So C could be, for example, the set of all intervals, maybe semi-open, semi-closed here, A and B again in Q maybe. And I can ask myself, what's this ring then here? How can I describe this? And we already saw that there is one property which makes this set system H only a semi-ring and not a ring, which is, we said, if I have A here, B here, C here, D here, the set difference of these two intervals, so AB without CD, is the interval from A to C, union D to B. And this union here is a disjoint union. Okay, that's why that's also a semi-ring. But what happens if we have this set here? They're all disjoint unions of intervals of this form. And what I say here, well, this set system containing all disjoint unions of semi-open intervals is exactly the ring which we defined here. So the ring generated from H. And in order to see this, there's a general lemma which I'm going to prove here. H is a semi-ring. Then the ring generated from the semi-ring has exactly this form here. Always, not only if H is here the set of intervals. So what do I have to prove? I have to prove that this here, the right-hand side, is a ring. And once this is a ring, I'm done, because, well, this ring here is the intersection of all rings, so that could still be bigger than this ring generated from here. But on the other hand, I at least have to generate all these disjoint unions. So every ring which contains H has at least to contain all these things here, because we said that rings are union stable. So I have to prove that the right-hand side here is really a ring, which means I have to prove two things. union stable and set difference stable. Well, so what will I prove? So let me start with proving. Let me start with proving intersection stable, because I will need this in the next step. So I claim that R of H is cap stable. Why is this? So that should be pretty clear. So how do I prove this? If I have this joint union here of some AKs, and I intersect this with this joint union of some BLs, well, here over K, here over L, I can write this here as the disjoint union over K and L of AK intersect with BL. And since H is a semiring, this here belongs to the semiring again, which means that I can write this intersection here as a disjoint union of sets in the semiring, which means that this here is intersection stable. So second thing is set difference stable. Here I have to write the disjoint union of AKs, set difference with the disjoint union of BLs, and well, that's the disjoint union of AKs intersected with room BL and the complement here. Well, but I can change this to well, this here I can write differently. Intersection and complement, right? Which means I can write this as in disjoint union AKs well, no, yeah, I can just use some usual transformation, KL AK without BL, right? And AK without BL can be written as a disjoint union. That can be written as a disjoint union. So that's in the set here, that's clear. The intersection of this here is also in the set here, as we just showed, because it's intersection stable as we saw, which means that I can write the set difference here as a disjoint union of sets within R of H. That was this here, and then I still have to prove that R of H is union stable. How does this work? Well, that's not so hard. A union B I can write as A intersected with B, disjoint union with A without B, disjoint union with B without A, which means I have written the union as a disjoint union of sets also contained in here, because I already saw that A without B is in R of H and B without A also, which means I've written the union as a disjoint union, and I'm done. So that's the ring generated by a semi-ring. And at the moment, I will not deal with the second thing, which is here the sigma algebra generated by C. But we will come to this in a second. But before we do this, I have to recall some facts from topology. Because we will define a sigma algebra here generated by some O, and O is a topology. And we will call this here the Borel sigma algebra on the set omega, or which is a topological space. So I will have that this C here is a so-called topology. And you already heard what topology is, I hope. And I will recall some things here. The manuscript has it a bit more general than I have here, but still. So topologies are also set systems. So O is a subset of the power set. If it's called topology if, okay, empty set is in the topology, whole space in the topology, it's intersection stable, and it's union stable for arbitrary unions. Recall for sigma algebras, we had this I here, the capital I here has to be countable. Here in topologies, it does not have to be countable. Arbitrary unions of sets in the topology are again in the topology. Then I call this here a topological space. And the members of the topological space, which are sets now, are called open sets. And complements of open sets are called closed sets. Note that a set can be both open and closed. For example, here the whole set. It's open because in topology, but it's also closed because its complement, which is the empty set, is also in the topology. Most often in probability in matter theory, what I'm doing here, I will have topological spaces which are defined by a metric. And that's maybe also what you heard in your first year of mathematics. So a metric space, you know what a metric space is, I'm not going to recall this. In metric spaces, I have something I call balls. So if I have some omega here, so that's the center of the ball, and I have a radius, which is the epsilon here, I have the points in the space, which have distance at most epsilon from omega. Then I have an open ball. And I have B. That's the set of all open balls of all radii which I can have. And as with rings and sigma algebras, I can have topologies generated by a set system. And this B here is a set system. And it generates a topology, which is this one here. Here it's like this here. So I take any subset of the set system, so any set of balls that I like, and I make a union of them. Then I have an arbitrary open set, because open sets are stable under arbitrary unions here. And then I have the topology generated by R, by the metric. I can also say it like this, and maybe you remember something. Well, I have a set here, maybe that's an omega, subset of R square, and I want to have a topology on this. And I know I have a metric on R square, and so I have a metric also on my omega. And the set is called open. Whenever I pick some center of a ball, I can have a radius such that the whole ball here is within the set. Then I call the set open. So the border here is not the part of the set. And that's why the first thing here holds. So for all omega in A, so this set here is my A without the border, there's some ball, and such that the center is in the ball, a subset of my A. So that's exactly this picture here. And that's the topology generated by the metric. We will need some things in our course here. For example, what is a complete metric? And you know what a complete metric is. That's a metric where all Cauchy sequences converge. What is a Cauchy sequence? A Cauchy sequence is a sequence omega 1, omega 2, and so on, such that for all epsilon exists an n, such that for all m and n bigger than n, the distance of omega m and omega n is smaller than epsilon. And as you see here, well, there's no limit, so there is no limiting object of this here. But I know that when I fix epsilon, distances can become arbitrarily small. So I find a capital N such that the distance is at most epsilon after this n here, which suggests that the sequence here can converge. But what's not so clear at the moment is if the limiting object, so the limiting omega or so, is really in the set that I'm dealing with. So that's a Cauchy sequence. And that converges if I find an omega. So conversion means I find an omega such that for all epsilon bigger than 0, there is an n such that the distance of omega, I forgot something. For all n bigger than n, the distance of omega n and omega is smaller than epsilon. So it's almost the same as here above, but here they have no limiting object, and here I have also the limiting object. And the metric is called complete if every Cauchy sequence converges. Let's say omega is 0 t infinity. And, well, r is as usual, r of x and y is just y minus x. Is this a complete metric? No, it's not, because the 0 is not in the set here. Xn equals 1 over n is a Cauchy sequence because, well, for all epsilon you find an n such that the distance between two members of the sequence is smaller than epsilon. Okay, that's clear. But this omega here has to be in big omega. And it would have to be 0, but 0 is not an element of the set here. So this sequence here is Cauchy, but it does not converge. So that's one thing I will need. I will also need separability, which is the following. So a space is called separable if there exists a dense countable subset. That's how you can call it. That's the following. I find a countable omega prime such that for all x here in my omega, I find x primes in omega prime which are arbitrarily close to my x. So for example, omega could be r, and omega prime, the countable dense subset, could be q. Then this here is the case. For example, if x would be pi or something, then I find rational numbers x prime which are arbitrarily close such that the infimum becomes 0 to pi. That's an important case in measure theory because in this case you can do the following. You can have all balls with rational radius around all points in the separable subset. And this here, so the B prime here is a countable set, because the omega prime is countable and Q plus is also countable. And for this reason, I can generate the whole topology O of B by sets in B prime, by this countable set. And you remember that sigma algebras require this sigma union stability, while topologies require the arbitrary union stability. And when you have such a separable situation, so a dense countable subset, there's no difference because it can generate every open set by a countable union of sets, like I say here. So these are two important concepts which we need, so completeness and separability. There's also a very special notion. A topological space is called Polish if it is separable and there's a metric generating my topology which is complete. And you can, for the most part, ignore this metrizable thing. You can just say omega is a metric space and the metric is complete and I have a dense countable subset. Okay, and with this, we now have recalled what a topology is, and we can come back to our sigma algebras and sigma fields, in particular to this definition here. So the sigma algebra generated by some set system, which could also be a topology. And if that's a topology, we call the generated topology Borel sigma algebra. So from a topological space, we find a sigma algebra, which we call the Borel sigma algebra. And sets here are also called Borel measurable sets. But for this, I really need a topological space. So for example, a metric space, the metric defines a topology as we saw, and the topology generates the sigma algebra here. There's one important thing that I just also mentioned. So if I have this separability here, I will typically have a subset B prime here, which is countable, which generates the whole topology. And that's the situation here. A topological space with a countable basis, so which means that this C here generates my whole topology. Then the Borel sigma algebra is the sigma algebra generated by this countable set. And for this, I need to show that O, the topology itself, is a subset of sigma of C. Why is that enough? I mean, I have to prove this here, but when I have proved this here, so which is pretty clear from the definition, when I have this here, I have sigma of O, subset of sigma of C, which means I've used that the sigma operator is monotone in the sense that if I have a set here, and which is a subset of a set here, if I write sigma in front of this, it's still smaller. That's clear from the definition, because I have a big intersection here, and this big intersection here so if this here is a bigger set, the intersection here is just over a smaller set of sigma fields that I can have. So that's pretty clear that holds. And another thing which holds is that sigma of C. Okay, what's this? That's the sigma algebra generated by a sigma algebra. But when you look at this here, if this here is a sigma algebra itself, it's also contained in this intersection here. So I can use the C itself here. But then it's clear, well, I just get my sigma algebra back. Which means that this here must be sigma of C. So when I have shown this, I'm done. But that's actually clear, because if I have an element in my topology, I know it can be generated by an arbitrary union of elements in my C, because that's a basis. But C itself is only a countable set. So A can be written as a union of B I in I with Bi in C. But C itself is only countable, which means that this union here can only be countable. But if it's countable, then it's also contained in sigma of C, because I just write it as a disjoint union, not disjoint, as a union, as a countable union of sets in the set here, and that's of course contained in the sigma algebra generated by C. So I'm done. Yes, so that's important things, that means for the Borel sigma algebra, you can restrict yourself to a set C if C is countable, and it generates the the topology here. So for the last slide now, let's look at our usual topology, which we have in R. Oops, on R. And we have a metric, right? We have a metric, I would say. R of x and y equals y minus x. This R defines the topology of all open sets, so the Euclidean topology. Have you heard about this? On the other hand, I have a set system, for example, like this here, semi-open intervals from minus infinity to b somewhere in Q, and I claim that this here generates B of R, which means what do I claim here? Sigma of C1 is the same as B of R. And I'm using this here. So the C here is the C1. And C is a subset of O. But I have to see that C generates the topology. I have to see that C1 generates the topology, the Euclidean topology on R. And then I can use lemma 1.8 and I'm done. So how do I see that this generates everything what I need? First of all, I can generate A to B as minus infinity to B without minus infinity to A. Yes. So I can write it like this, that's clear. I can also write AB with opens here as a union, I from 1 to infinity, from A to B minus 1 over n, 1 over n is not good, only if I have an n here, so that's the same. And that means now I can write AB using sets only in C1 by having set differences and countable unions. And these sets here, of course, they generate the Euclidean topology because these are just balls. So they here, yeah, so that means that I have a C here, A, B, A smaller than B, A, B in Q. So they here have the desired property to be a basis of my topology, of the Euclidean topology. I can generate these here by set differences and countable unions. So yeah, I have sigma of C equals B of R. But sigma of C, on the other hand, also is just the same as sigma of C1. Because as we saw, from C1 I can generate all sets in C, and on the other way around, all sets in C I can generate all sets in C1, such that the sigma algebras of the two generators must coincide. So I have proved what I wanted, and that's all for today. And in the next video we will have another set system which will be important later on, which are so-called Dynkin systems and also compact systems. See you then.